Thank you, Sanjay, and thank you very much for letting me be here on the 10th workshop. One of the things that Sanjay pointed out was that when I was in Indiana, we worked on a project called PC++, which took the language approach, and your approach outlasted us by about 19 years, I think. So the approach to extend functionality with a language is very hard, and that's actually one of the things I'm going to talk about a little bit in my presentation today. And because we're a small group, please feel free to ask questions. I'll be asking questions of you, so it's only fair that you ask me some questions as we get started. I've been working in this space of trying to get Exascale going sort of internationally, so I thought I would just give a couple quick words to let people know, around the globe as we look toward the next generation of computing, what are people doing? And Sanjay pointed out that when we first were working in parallel programming, it really was, 64 processors was a big deal. And there was a couple workshops at that time, and they named one of the workshops, I remember, the Frontiers of Massively Parallel Computing, which at that time, massive was hundreds or maybe even up to 1,000. And now we're looking at that being the size of feature in a socket, right? 1,000 cores on a socket. So let's talk about what's happening here internationally. So there was an effort several years ago to bring together the groups internationally and just sort of do a little bit of planning. It was called the IESP, and there's a number of white papers and a roadmap at a website that we created called exascale.org, and you can go there and take a look at some of the roadmap materials. But the U.S. began that push, and so did Europe, so did China, so did Japan. Now, Europe has actually launched something, and it's very exciting. I have been to Europe a couple times helping them with the planning efforts for their Exascale work. And this is a press release here in the U.S., or actually in the U.K. here, which is to show that the plans, at least in Europe, is to double the funding in HPC. So for those of you looking for postdoc positions, that might be a good place to start looking, as well as the U.S., of course. This is, of course, the Barcelona Center, only put there because it looks good, but not because it's important for the press release. But they also have started 3 projects there in Europe that are hardware projects and software projects. And they're very interesting, and I'm pretty excited about them. There's reasonable money to get. This is just a bootstrap a process. Now remember, the Europeans have already started. The United States is still behind in this regard, and I'll tell you about our status in just a moment. But one of the projects here is what I find very interesting is this project here called Mont Blanc, and it is designed specifically to create an all-European supercomputer. So this is let's use all the tech we have spread about Europe. So they are using ARM, which of course is the processor that's in your iPhone, right? So this is not a small processor company that may or it's not a transputer. Let's put it that way. This is a company that is at the top of mobile technology in the world, and they're going to link that with a company that actually fabs things. So if you want to buy an ARM chip, you might be able to buy a small board that comes from ST Micro, a European, a French, and Italian company. And then Bull is an integrator. So this will be a design to prototype, at least explore an all-European technology supercomputer. There's also a group working with Intel and another group working with Cray. And the Europeans have made recommendations that a couple $2 billion be spent on exascale computing. Now, the purpose of this is really economic competitiveness. In the U.S., the push toward exascale is really focused because it comes out of the DOE on science objectives. But this is very clear that the plan is science along with economic competitiveness. Now, a couple weeks ago, I was in Japan and got to see the K computer, which is the Japanese computer that's right now the fastest computer. They have this fantastic building here, this Institute for Advanced Computational Science, where the K computer lives. And it's a mammoth computer, just absolutely monstrously large, 800 some cabinets. It's not so densely packed as our Blue Gene Q that we have at Argonne, and I'll talk about in a second. But it is very, very stable, and they've worked very hard at resilience within the system. And it's a fantastic accomplishment. However, you know, you've seen one supercomputer. You've seen them all. You know, you take a tour. Hate to say it, but you take a tour of the supercomputer center. It's a bunch of racks, and it's loud, and it's cold, right? So that was not what was most interesting about the Kobe Center. So this is the view. There's a nice viewing room. You can't even go down on the floor to look at the machine. These traffic cones here were placed there on purpose to be a visual indicator to tourists who are visiting that the machine is not in production yet. So don't expect it to be solving the world's problems yet. So there's a lot of press that is there all the time. While we were there having our workshop, I was interviewed for the local television station and so forth. This is a big accomplishment for Japan. They're very proud of it. But the exciting part was what was underneath the building. So I realize this is a computing talk, but you gotta appreciate the engineering that went into this building. So in order to keep this building isolated from earthquakes, since it's on an artificial island, okay, that's already a bad start if you're trying to avoid earthquake problems. The entire building is resting and floating on pads. So this is a rubber cushion. That's my hand there. So the entire building is sitting on rubber cushions, isolated from the walls even of the earth that comes up to it. So there's a gap between the wall, the ground, and the building. So to get into the building, you literally like cross a little. There's some stairs, but it's like crossing a bridge because the building is sitting on these isolator things. And then there are more of these, and you look at this and what is that? Well, that's not holding up the building. These blue bars here are for when the building does start shaking. You're deforming those blue steel rods, and it dampens the shake of the ground. Actually, the building's not shaking, right? The ground's shaking underneath it. And then this, I thought, oh well, that's like a rubber hose connecting one part of the building to the other. So if it no, this is actually solid lead, and this dampens the building in another way. So that you have damping in one way and damping in another direction or another type of wave for the earthquake. So the Japanese have invested quite seriously in this, and right now they're looking at investing in the next generation of exascale computers. The coolest thing about the tour was that I did get to tour underneath. I was the first Westerner, and I think the only one so far, that actually got to sneak in with the designer of this underneath. And it is a cavern underneath. It takes 20 megawatts or so to run the building. It's quite fantastic. Of course, China has also pushed very hard on exascale and on the next generation of computing, and they have their own chip design, the Godson, which is a multi-core that looks like Blue Gene Q, that looks like Knight's Ferry. So all of the major areas of the world are working on the next generation technology, and it's quite exciting. The Europeans have already started some projects, and the US is getting started. So after years, it takes us a while to get started with the planning. Eventually, my hope is that we outspend everyone, but at least we'll get started slow with the planning. And 24 senators, including the 2 senators from Illinois, so we're very happy about that, signed a letter to President Obama saying, you got to start exascale computing, a push toward the next generation of hardware and software. You get 24 senators, both red and blue state senators, to sign something. It's a pretty good and positive thing. So we're pretty excited about that. So what's it all going to mean? Well, we have the machines that we're deploying now. So right now we're deploying a Blue Gene Q at Argonne, and we have, I don't know, is it 16 racks? How many racks are like on the floor now? 16 racks are on the floor. The Blue Gene Q was designed as a partnership with Argonne and with Livermore Laboratory, and everyone got in the room together to design the machine. So that's really a nice thing. People have been calling this co-design, but it really does mean that we get to sit down and argue about what goes in the chip and what the software does. So let me give you an example of that argument. We have enough power on the chip to give you 18 or 19 cores. But we can't give you 19 cores if we also give you an MMU. So would you rather have 19, 20, cores, or would you rather have 17 cores and an MMU? Well, okay, so that's something to think about. We want an MMU. We would rather be able to actually have reasonable page handling and memory mapping than treat it all as physical space, essentially. So, but those are the kind of trade-offs that you get to do when you're working to design the system. The same is true for the power management and a bunch of other features we'll cover. So each node has 17 cores or 16 cores that are planned for computation, the 17th for service daemons and so forth. And it's getting set up. It is very densely packed, unlike that K machine I just showed you. These are the rack, a single board. Unfortunately, IBM calls it a node board. And so these are node boards, but these are nodes, and the nodes are water cooled. And so there's a bunch of plumbing underneath here that circulates water to cool everything. And in the end, it will take on the order of a handful of megawatts to run this machine. A question? So the K machine uses water cooling as well in some parts of the machine, but there are other parts that are air-cooled. And so the reason that they have this cavern underneath with all this air flowing through is they have to mix that in a pretty inefficient way. The Blue Gene, on the other hand, all of this is water-cooled, so it's all tightly packed, including water cooling, these sort of pipes up to the optics. But the only thing that's not water-cooled are some of the power supplies, and that needs just a little bit of cool ambient air, not the kilowatts, 100 kilowatts a rack or something for the rest. Okay, so now let's talk about what's happening, what we've learned, and how it will affect system software, which is what you really care about if you're here at the workshop. So the U.S. is now working on getting bids from companies for processor technologies, and those bids are due in 3 days. So if you're a processor company, it's too late. So those request it was followed into it's two phases. The first was a request for information. In other words, what is possible? So the way you do this when you're developing new technology is you first ask the question, what's possible? You can't just say I want to buy X if it's not going to be there. So we did what's called an RFI. That's the ask what's possible. And so we presented this roadmap and said this amount of time where we expect, I don't know, into the 2022 now, I think is where we are, to deploy a super very large scale machine. And these are the goals. The goal is 20 megawatts. Now that is the key figure of importance in all of these designs. Remember that the K computer that I just showed you is already using, I don't know, I think maybe it's about 12 megawatts for just the compute part. And it's a factor of 100 away, right? So if you just scaled the K computer, you would, be nowhere near a target for an exaflop of 20 megawatts. Similarly, the machine at Argonne takes about, you get about 2 petaflops per megawatt. So it's pretty far away, even though it's a much more efficient design, probably by a factor of about 2. So the real hard piece technologically is power. We can't build, University of Illinois can build 20 megawatt machine rooms all the time. And certainly if you ever want to upgrade the machine you have now, you don't want to have to upgrade the power again. I think it's plumbed for like, what, 25 megawatts or something to that effect. How much? 25 to the building. So you really can't afford, if you're going to keep adding supercomputers here at Illinois, to keep adding more power. So power is the fundamental constraint. Okay, so when we talked to all of these companies and we got their secret NDA plans for what is possible, we realized some things that are very important. So the first is that parallelism within the node is dramatically increasing. You knew that, but I'm going to talk a little bit more about that. That means the system software has to dramatically change. We also learned that dynamic power management is critical to performance. All of the companies said we have to be able to manage power as a constrained resource. So system software will change to do that. We also learned that for distributed memory, cache coherence is not power efficient. It would be very good on a chip if you could just break cache coherence and say, I'm not going to be cache coherent for this section, and you'd save a lot of power.
When they say crucial, are they willing to see that software?
Yes, they are. And I'll say what I can without getting in trouble about that.
So another thing which is related to this power issue is the very, very deep memory hierarchy. So the cost of moving data is the power cost. It's actually a bandwidth cost. And so you can move it from here to here, it's pretty cheap. Moving it from here to way over there is expensive. So adding lots of hierarchy helps with that, because then you're just moving it only as far as you need to, right? You're not moving it out to main memory or even out to cache and back so often. So that's a power issue. And one way to address that is with 3D stacking memory. We'll talk about that. And faults may increase. This one is a little bit squishy. You know, a lot of companies saying they think they have ideas for how to handle fault, but we'll get there. All right. So let's talk about parallelism first of the list. We'll try to go somewhat quick. Now, this is an old plot, but it shows the parallelism in the top 500 systems. And one of the things that I think is remarkable is looking at this section from 1997 to about 2003 or 4, was that the amount of total system parallelism in these supercomputers didn't change. That means that, I mean, really, when you think about this, it's quite amazing. It means that applications that scaled to the full machine here had a run of 8 years where they did not have to do anything to their code. They just had to wait, and the machine got faster. Okay? Now, of course, you know, we're on this exponential, where the parallelism is doubling every year. One of the things that Andrew Chen mentioned this first, it was kind of fun. He said, you know, when I first went to school, they were talking about the thing that you could see as being a transistor, right? And then eventually it gets on the die and you can't see a transistor, right? You know, you can see, now you look at it and you see the whole chip. You can no longer see the transistor. It's invisible. It's too small. You only see the chip. And now we're at the point where you can no longer see the core on some of these machines. It's not just the transistor. The core is almost invisible to the naked eye, and you're amassing cores. So we're going through this transition where we're adding parallelism here, and this makes it very difficult for the programming model, which we're going to talk about in just a minute. And so if we look at that very first item, parallelism is doubling every year, we're now in a place where, okay, well, from a system software perspective, how do we address that? Well, you might look, okay, let's look at one of our current solutions. One of our current solutions is OpenMP. Right? This is a language approach. And I stole this, this chart from Livermore. Now, Rob Neely is not here, so I won't shame the Livermore guys too much. But this is a chart which tries to explain the directives in OpenMP. So this is how complicated it is to write something in OpenMP. You know, this is, you know, a parallel or a do for will work with this feature but not with this feature. A sections directive will work with this feature but not this feature. this parallel sections here will only work here but not work over there. If you're a programmer, the fact that this is in the guide is already amazing, but this is not a way to write parallel programs. It cannot be a way. If it's true that parallelism is doubling every year and we need ways to abstractly define the work to do so that the runtime system like Charm++ can do the work underneath, we can't have complex structures like this in our code and then be able to update it for the amount of parallelism that's an exploding quantity. So we are in a bind here. We don't have a good in-socket parallel programming model unless you go to a runtime system. The current static model here is not working well. And we know that there's going to be deeper memory, more scratch pad. I mean, this approach from a static software language perspective is pretty not looking very promising. So, but the real issue, and let me just be computer scientist for a minute, is that this is changing our model for the abstract machine. Now, this is where I ask you guys a question. So this is a sort of an artist rendition of a Turing machine. Hopefully you recognize that. The infinite paper tape on each side and the head that moves left and the paper moves left and right and the head that writes zeros and ones. Okay. So when we study algorithms like bubble sort, quick sort, and so forth, in your analysis of algorithms class, what is it that you measure for an algorithm in order to tell whether it's a good algorithm or a bad algorithm? So let's look at just bubble sort. So bubble sort's order n squared. Order n squared for what? Lines of code? No. Okay, so you don't measure lines of code. So what do you measure? Comparisons. Okay, so you measure comparisons. So our model for the abstract machine for sequential, for all of your analysis of algorithms class, you start and you say, okay, we're going to compare these algorithms based on comparisons. Okay, well, we just start talking about the future hardware that we're going to get where the cost is moving data and power management. So you might argue that comparisons come for free. That from a energy perspective and from a speed perspective, you could do as many, you have a sea of ALUs. You could do as many comparisons as you want. It's going to be all about data movement. So the question is, have we imagined or considered the abstract machine model for even analyzing our programs where it's data movement that is the confining operation, right? In that case, is quicksort or bubble sort better? I'll leave that up to you to work on later, whether from a data movement perspective. So as we change the machine, fundamental pieces of computer science are going to change. This notion that we count flops is going to leave, right? We just won't care because it's about data movement and it's about power management. Now, that's at the abstract machine level for a single processor. We also have this problem here, right, which is the parallel machine. Now, this is meant to represent something that all parallel programmers believe is true. Equal work is equal time. So the very first thing you do as a parallel programmer is you divide your program, domain decomposition. Well, what do you do in domain decomposition? Equal work. I'm going to divide my program into a bunch of equally sized chunks. I'll assign them out. When all the equally sized chunks finish, I'm done, right? But we know, and Sanjay's work and the Charm++ team has been doing this for years now, know that equal work is not equal time. There's temperature, there's power, there's fault, right? And all three of these we know in future machines are the constraining pieces. So from here teaching at the Siebel Center here, right, when you teach parallel programming, the very first thing you should tell students is equal work is not equal time. It's going to be different. It's whether now the question is we have to become like physicists years ago moved from classical physics to sort of quantum mechanical where you're talking about distributions. Computer scientists have not done that yet. We don't talk about the distribution of time that a work element takes and that we're programming for a distribution, but that's really where we're going to be moving. So the abstract machine has to change because of this power constraint, and the parallel abstract machine cannot be based on equal work is equal time. Now, fortunately, as you know, the runtime system you guys work on is already a large part there, an understanding that it's about moving work items. Okay, so what's the solution to this? Well, there was, years ago, lots of work on parallel programming models, including things that did graphs and even, hate to say, functional programming, right? So there are a variety of things in our past that we can look at that hint at how we should be doing task-based, DAG-based, recursive decomposition to give us the parallelism that we want, and also to understand that work items do not take equal time, that you can do decomposition, and it's going to have to involve load balancing. So there's a lot of previous research to look at. But we really will need to reinvent the programming model here. Charm++ has done that for one type of coding, but this notion here where you have memory, processor, and a link, this will probably stay with us. Even with all the changes I mentioned about power and cores and constrained resources, the basic future machine will probably still look like this. Some memory, some cores, and an interconnection link. So we really have to look at changing how we program that machine, if this is our abstract machine model, how we program that with dynamic workflows and so forth. We really have to return to higher level models rather than the equal work is equal time model, right? This what people generally refer to as bulk synchronous computing. So from the system software, our challenge is to explore a new abstract machine and languages and runtimes, and OpenMP, which really is a equal work is equal time sort of approach, is never, ever going to get us there in terms of scaling. It will have to be something else. Now, whether we need a new language or not is probably an interesting question. It may not be a new language. Mark Sneer likes to say that it may not be that we need new syntax in order to represent a new programming model. And that may be the case here, that we can address these from another perspective, whether it's a language or a library or other extensions. Okay, so let's look at intranode programming now for just a moment. That was sort of a broad piece. Now let's look at the power issues inside the node, and cache coherence, something I mentioned earlier. So I've divided the world into sort of now, somewhat forward-looking things, and then looking out to the future. So right now, on these machines here, the IBM Blue Gene Q and the Intel Knights Ferry, and at Argonne we have a Knights Corner, these machines are still cache coherent. Now the designers, as I said earlier, the designers tell us that that is very power hungry. We want to get rid of cache coherence in areas on the chip, making even deeper memory hierarchies. So if you look here, the Intel chip, this was they called it their cloud computing chip, but these were independent tiles which did not share cache. Tylera makes a chip, and Adaptiva make a chip that have sort of squishy coherence protocols that allow you to get more cores on the die, but also not have to spend the power or the communication on coherence. But that means that we fundamentally change how we look at a node. We're not looking at it from the Linux SMP sharing all the structures perspective, but we have to start dividing up the operating system and the system software into coherence islands, right, where there's coherence among this set, and then you're actually passing messages between sets of cores. So this is a reference to an old sci-fi movie. How many of you have either read this book or seen the movie? Come on, don't be shy. All right. Okay, maybe not quite as exciting as Avengers, but it did have Raquel Welch and some other stars of the day. So the point of this, it was actually a book that then later Asimov helped sort of spice up and recreate to end up with a movie. But in this movie, the first of its kind, they shrink down a spaceship, essentially a ship, down to nano size, and it gets put in a body, and they're intending to float around the bloodstream and fix a blood clot inside a body. Now, the interesting concept for this movie is that the things that were imagined for outer space become completely normal and used in the small in inner space, right? So these guys have spaceships, laser weapons, and spacesuits, right? But they're shrunk down. So this concept is actually the same thing that's happening in system software. So in the system software, the outer space view of passing messages between nodes, of not having coherence, of assuming another node is down and can't be connected and is offline, that same programming model which you're familiar with in the large is what it looks like will be shrunk down and be in the small. So inside our node, we expect outer space to become inner space. We expect to pass messages between coherence domains inside the chip. We expect to pass a message to a set of cores and have them not be there and be dead and offline, just like we do with the sort of resilience protocols that we have in the large. And we expect, yeah, go ahead. That's a good question. So the question is about, will the HPC market sort of be a divergence point for this coherence? I don't think it will be, for the reason that we're all looking for more power in our smartphone, and that is really what is driving the power down, is the need to have battery-powered devices, right? For your home, you've got your laptop plugged in. Your desk side plugged in. It's not such a big deal. So the vendors like ARM and others will be looking for ways to give you more flops and more video processing and more game processing, even if it's at the cost of not having a simple programming model where everything is connected with coherent cache and so forth. And you can see that already. Some of the iPad and other devices have codecs that are set up that only they essentially have windows on memory, right? And then they're just streaming that from that window out to the device. So this model of what was outside programming is now inside programming is what we will likely see, and Charm and other runtime systems will adapt to this. So in this new realm, power becomes a managed resource. We have more functional units than we can run at full speed. One of the things in working with Intel on the Knight's Corner and trying to get that set up, several of their presentations talked about TDP, within the TDP, and that was an acronym I had never heard before, and it's the thermal design point. So these chips are designed to be able to, put 35, 40, 50, whatever watts out, and that's it. You could run it faster, but it's going to be, as we saw in yesterday's presentation, it's going to be throttled back until its core temperature, until the temperature is something reasonable again. And so that thermal design point is what limits how many flops you're going to get out of a system. Now what's cool is the new chips are coming with power domains that let you turn on and off cores and change the frequency of cores at a per core level. So you can imagine a chip now, and this is what's really fun for runtime system folks. If you're looking for PhD topics, it's a mass of cool things that you could do in a chip where individual cores can be sped up and slow down to respond to demand. Yep.
The commercial processor that in the present market has distributed, or
yes. I can't tell you which one, but the answer is yes. And the plan is for it to be generally available to the market in about 8 months. So but right now it's available for testing in various venues. So you have to look at where the new chips are landing, and the new prototype chips from Intel, NVIDIA, AMD. Those are the three big companies, right? But this idea also allows them to move the memory from M0, M1, M2, M3, and the processor from C1, C2, these different power states, right? So this is really exciting if you are a runtime person. If you're working on something like Charm++ or something else, and you want to be able to vary the speed and therefore the parallel efficiency based on load, this is a very exciting time that we're about to enter. And it really will mean, that's why I asked the question yesterday, has anyone seen the case where you can adjust the power to increase performance? And that's really the key that we're most interested in. Yes, we want to save the planet and reduce power, absolutely. But what's most interesting is managing the power within this thermal design point. So you're given 50 watts. What can I do to make the chip perform better within those 50 watts? And that is the key question. That's the one that's most exciting, I think, for us. Okay, so we've been doing some power experiments at Argonne. We've been doing these power experiments on both Blue Gene P, Blue Gene Q, and Knight's Corner. These are just a few of them to give you a feel for things that's kind of interesting. So this was a long time ago. This is now like 3 years ago, I think we did this, which was, this is a simple scatter chart of jobs on a half rack and how much power they take. The point of this graph is to show that jobs really did take different amounts of power on Blue Gene P, even though the clock is sort of fixed at about 700 megahertz, or 850, is that it, on Blue Gene P, that they took different amounts of power by about a factor of 3 from idle to full-up QCD or LinPack. And the future machines, Blue Gene Q and others, are in that similar space. This was a piece that we did on Blue Gene P as well, which sort of divides up where the power is going. So here in blue is the CPU and memory, and then there are other things like the link card and CPU usage. So this is just the idle power. And with these older chips, what we're recognizing and realizing, it's kind of disappointing, is that the idle power is the large fraction of the overall power. In other words, these first generation chips that we already have and already been using, they vary from, let's say they vary from 35 watts to 50, right? They're not varying from 0 to 100. They have a very high idle power. Now, the next generation of chips does have a lot more variability. And in fact, what's on your cell phone, when it's not in use, it drops down to practically nothing, right? That you're just using the clock. Yeah.
Hi. This is more than 940, so okay. But the other point is that the scatter plot. What are the two dimensions?
Yeah. So one dimension is power. Okay. Power for midplane, and the other was I believe it was how long. Yeah. How many hours the job ran. So we wanted to kind of understand, is it all sorts of jobs? And really, because the distribution this way is even, it's really the fact that most jobs in this dimension are taking this amount of power, which was 80 kilowatts or whatever. So this is from Blue Gene Q, I believe, and is just very recent. In fact, we haven't published this result yet. But it shows the different power domains on Blue Gene Q. And in particular, let's look at, we're doing some floating point operation here. And you see in blue the total amount of power used, right? And now if you look in red, this is the core. And, well, let's see, there we go. And then here we have the power domain that includes the memory. So in this case, for doing floating point operations, you can see that the memory is only slightly used, and it's the floating point ops that are sucking up all the power. But now, this is a benchmark that Kazutomo wrote that just exercises memory. And you can see that, well, the idle power of the floating point unit is pretty high. So even when you're not doing floating point, the idle power is high, so this is not a big difference. But the memory really did double its power, right? From here to here, that's about doubling the power draw. So, yeah.
How did you measure the different domains? How did you get to
with a lot of phone calls with IBM. So because they built the machine for us, we have access to their engineers, and there's an FPGA on the board that runs and gathers data about the different power domains that we were able to
get information from. The thing that's most interesting about that is we started doing these benchmarks and saw that the data that we got was shifted from reality by 7 seconds. So it's like the 7-second delay, right? And so when we finally, waded through all of this with IBM, all of these systems are gathering information independently. So there's something that's gathering information about the power domain. It eventually bubbles it to another processor. It eventually bubbles it over here. And then eventually it gets to a place where a control register can read it. And that took, literally wall clock time about 7 seconds. So we have to now, pad all of our experiments so that we can try and get the actual measurements with that in mind. Okay. So we've also been doing some experiments just using a simple infrared camera to kind of understand what's happening. So these are two Knights Ferry boards, and you can see here that why one board is getting more power reading than the other board. It's significantly hotter, and it looks like it's really an airflow issue. In this case, the Knights Ferry boards, I don't know if you know, have a fan on the side. The air intake is here and goes out here. Well, this one has no air intake, so this chip is getting hotter. So there's also packaging issues as we try and debug these things and try to measure power and understand what's happening on the system. And as I said, we're doing a number of experiments. This is blotted out here because it's still NDA from the Knights Ferry, but looking at what's taking the most power and what kind of experiments we can do to exercise components. Now, why are we doing all this, okay, in terms of the power measurements? Well, as we look to the future, where power is managed, as I mentioned, you could actually turn cores on and off, change the amount of memory that is accessible. Now we're going to need to understand this model so that we could then work on algorithms and runtime systems that maximize performance by managing this constrained resource. So that's what we're shooting for. I mean, it's going to be a couple years probably before we get there, but it's an exciting area for us. Okay, now a couple words about sort of near future technologies, what we're seeing on the horizon. So there are two things that are very interesting, I think. The first is this thing that Intel is talking about, this near threshold voltage. Have you read any papers yet about this? Have you seen this? Oh, good. So we'll see how many of you took your electrical engineering class. So what voltage do you need in order to flip a transistor? To forward bias the base emitter junction, right? Yeah, 0.7. Ooh, did you take an electrical engineering class? Computer engineering. Computer engineering, awesome. All right, so you need about 0.7 volts on the base and emitter in order to cause it to open up, and you get a 1 essentially, right? For computer guys, right? It is an analog device. For us, it's not an analog device. So to get a 1, you need about 0.7 volts. We run them typically at something much higher than that. In the past, 5 volts, 3 volts, 3.3. tweaking down lower and lower. So the question is, and Intel is asking the question, well, how close to the threshold voltage can we get? And if we get really close to the threshold voltage, well, of course, now you have a higher probability for single bit upsets, for having it just sort of, oh, no, it's one of these. No, I'm wrong. It's one of these, right? It's a 1. No, it's a 0. No, it's a 1, right? So flipping back and forth is a problem. And they're also slower at that voltage range, but you get tremendous power savings. So this is a notional graph. I mean, Intel is not going to share the real data with any of us, but this is a notional graph showing the voltage from 0 to max. So there's no units on here, obviously. And showing energy efficiency from low to high. Oh, again, not so helpful. But the interesting thing here is that in this near threshold range, they're getting a 5 to 10x improvement in energy efficiency. So if Intel is designing chips that have a lot of variability, and then they demonstrated that the chip can go not just from 100 megahertz to 110, right, which is sort of where, or 2 gigahertz to 2.1 gigahertz, which is where the power turbo boost sort of range is, just a little bit of play. They're going from 3 megahertz almost up to a gigahertz, right? So this is a dramatic dynamic range, and with that dramatic dynamic range, you get fantastic savings. So,
exactly.
To the near threshold.
Yeah, and so
again, the question for us system software weenies, right, for people writing code, is okay. So what can we imagine? Again, what can we imagine in the runtime system that would allow us to vary this in a very dynamic fashion? Possibly, on the, depending on what, maybe this gets down to millisecond times. Maybe it's much faster than that. Maybe it's hundreds of microseconds to be able to adjust this, and then really attack the power problem. And remember, power is directly then corresponds to what kind of performance we can get, because we're operating within a thermal design point. We're trying to get the maximum amount of work we can do for a certain amount of power. The other thing that they're looking at, and this is really, the math library guys, to get their heads wrapped around this is really hard, is looking at variable precision floating point. Again, simply to save power. Again, from our perspective, right, if it were up to us, you would just declare everything a double and be done, right? Okay, I declare my program, all my variables doubles, and I don't worry. But if you're power constrained, choosing your precision will affect the speed and the power, but most importantly for you, the speed. So we all know already that some chips are having twice as fast with single precision, but now imagine that you can dial it to several layers. You have 12 bits of precision, or 24 bits of precision, or 48 bits of precision. So now imagine, again, if you're a library designer, system software designer, that we've generally handled this with code generators that generate a single precision or a double precision version of the library. But now the right thing to do is to ask the user, when the user calls a math library, what precision in the answer do you want? And then the right data types, the right types are used in the computation. So in Klaus's code, what should happen in the future is that for a particular function, the precision required in the answer is what you pass in along with the basic parameters. And then within the chip, the right decisions, and within the runtime system, the right decisions can be made. This will radically change how we write system software, especially math libraries. Okay, another thing that's happening is 3D chip stacking. Now, you've probably heard about this, but Micron is now getting more and more public. Sanjay and I were just at a presentation a week and a half ago, 2 weeks ago, where a chief architect, one of the key architects at Micron, talked about the hybrid memory cube. The hybrid memory cube is this thing here, and these lines are these through silicon vias. They're think of them as channels, not quite solder pipes, but they're connection channels that go vertically through the layers. And the Micron guys wanted us to be clear and understand that this is not drawn to scale. It's not really that high. These are wafers that are very thin, stacked on top of each other. But the point of this is that by putting all of the memory that your application needs on the die, on the chip, the whole memory wall thing that people have been writing papers about for 10 years now goes away, right? There is no bottleneck between the CPU and memory in this design. However, there still is the power bottleneck, which is if you plan on, just like those pictures Let me go back here. So if you plan on hammering memory, right, here in yellow, if you plan on hammering memory, then you'll pay the power cost, even if it's in package. And that may be a limiting factor for the code. So power management is going to be critical. The other thing, though, from a computer science, from an architecture, if you've taken an architecture class, that is most interesting is that once you take all this memory and stack it up, you can put as part of the logic board that sits under the memory a little bit of processing. So this means that from a system software perspective, it may be possible to have essentially pieces of code that execute in the memory controller. So doing atomic increments, chasing down linked lists to finding things, could be things that you assign the memory controller. You give an instruction to the memory controller, chase this linked list down and append this value, right? Do a sum of these important numbers, or do a what were the items that you wanted, Jeff? 1 over x, 1 over square root of x. What are the functions that you want? All of them. What's all of those functions, right? So, so this is again a real change for system software. Is imagining changing what the runtime system can do, in imagining that there are operations that you could assign another piece of hardware, which is memory traversal hardware. So these advanced memory operations may be possible. And then this really changes this memory management. It's not one big, huge, flat memory space, but it is tiled up. It is not coherent across the entire space of the operators working on it. And power management is still an issue. Now, those other pictures here are drawings, right? Recently, there was a paper published by some guys at the University of Michigan. This guy is, I've been talking to the professor there. His student has graduated, so the hardware already doesn't work. But for his PhD, they put together this 3D chip stacking, and so it is possible, even in a laboratory at a university, to put together these sort of new chip designs. Now, I don't know if you can see this, but of course you always take pictures of chips on a penny. So they've got Lincoln's nose in 1997 to help you understand how big the chip is. And what they've done is they've stacked up. I think there were 64 ARM cores plus some memory in this device. So these sorts of stacked devices are our future in system software and system programming, to be able to manage that many cores and the memory with it in a power-friendly way. And, of course, we may be looking as well at non-volatile memory and whether it's Memristor or PCM or something like that. So, again, new algorithms that read more than they store. So this is another quirk of the hardware. So the way phase change memory works is it's the same. Essentially, it's the same material that's in your CD-ROM. That's a burnable CD-ROM. So the way the burnable CD-ROM works is, you heat it up and you can change it based on how you heat it up, how reflective it is, its index, and you can do the same thing of heating up one of these things and change its resistance. And the interesting thing is that reading it is very cheap from a power perspective, right? Because you're not heating it up. Writing to it is very expensive from a power perspective. You actually have to sort of melt, you change its structure, heat it up. So that means that from a power perspective, we can imagine algorithms, and there'll be a whole set of algorithms that people will design where you trade writes for more reads, right? Because reads are power efficient. Writes are not power efficient on this kind of hardware. And so you might create pre-compute huge tables which you're then reading from. I mean, go back to the log books, right, where you're calculating a log by looking it up. So you can imagine looking up these things because it's very cheap instead of writing. And so this is, again, a very exciting place for system software. All right, so fault, we really don't have a good handle on this. I'm not sure exactly what to say. It is so uncovered so far in our system software. We worked on a project called CIFTS, which worked on connecting different parts of the system into something we called a fault-tolerant backplane, so that the processor could talk to the job scheduler, could talk to the MPI, could talk to the linear algebra library, and so forth. But this is still pretty primitive. We're really going to have to drive down into the runtime system, into the low-level OS, these notions of fault and response. So let me wrap up here. We're in pretty exciting times. This is a very fun place to be for a computer scientist working in software. The parallelism is dramatically increasing, which opens up a lot of areas for research. Language-based versions are going to be tough for a while because of this doubling of parallelism is very hard to handle at the language level. You really need something that's much more adaptive, a runtime system. Dynamic power management. You ask a question of what chips are available now that can do this. Come talk to me later, and maybe we can get you on a machine that does this soon. There are going to be in the next 6 months to a year chips that you can adjust the speed of cores and turn them down to 0 or turn them up to max, and that will be very exciting for system software folks. Distributed memory, this cache coherence issue, and maybe even be able to predict it or set it at runtime. So you might boot a chip and say, I'm willing to pay the cost of cache coherence. Or you might say, I'm going to tile them in groups of 8 and only pay for coherence within the groups of 8, and then I get better performance. These deep memory hierarchies in addition with NVRAM and phase change memory, and of course faults, as we know. And there's several papers now of people talking about protecting operating system pages with checksum bits, and protecting control flow structures with different things. I think this is still a space that's going to have a lot of churn for a while, but interesting research topics. So I already went through these. For computer science, it means a lot of new things, and I think that's it. So with that, I'll take some questions. I think I did mostly on time.
Before we ask questions of people, I have a question for you. How many of you got the large table reference? How much did you watch? Okay. Those are gone even when people got covered. But questions?
Yeah. Can I ask you about floating point? IEEE 754 is my friend.
Yeah.
And sometimes more important than the precision is the error characteristics.
Yeah.
Right.
Yeah.
So the unbiased rounding can, particularly with something like Klaus does, and also when I do if you have biased rounding at your floating point, it's a disaster even more. That people thought about the error distribution. Oh, and the other thing is sometimes I want double precision, not for the mantissa, but for the exponent.
Yeah.
So if people thought about...
So I haven't seen it. I'm sure that people are looking at whether there would be standards or whether companies, what happens generally, if companies make this an advantage to them in some way before a standard, right? So they're going to provide some new feature which allows a cell phone company to write a codec that does some interesting thing at a lower power, right? And so it may be some time before it's standardized, but I think you're right that there are a number of issues with respect to where the error actually is, and is it unbiased, and what kind of distribution it is that I think we haven't seen yet in their solutions. And Intel is just starting to play around with this. I'm sure other companies already are.
I had a comment, which was, I think IEEE is not your friend, because a good numerical analysis could probably, if they work really hard, you get way more performance out of going to reduced precision than you do by paying for full double 754. But second thing I'll tell you, which may be fun, is that BlueGene-Q supports, it's disabled by the OS, but it actually supports in hardware random rounding, which is, in terms of distribution, is interesting because it should be a flat distribution that is truly random. And actually, so one of the guys I talked to a lot at IBM said that he used that to evaluate the numerical stability of his algorithms, because you can obviously do single versus double, but that's sort of a big, wide window that doesn't tell you much. And what he did is he actually said, well, if I flip the random rounding bit and it doesn't change it, then I really don't need 754, because the last bit, as long as it's not biased in one direction, doesn't matter to me.
Well, so 754 didn't talk about the biasing, right? That was
topic for discussion in the week. I should suggest that can we just postpone that so that we get other questions? Yes, Ferry? Oh, fine. Thanks for reminding me. Okay.
So you described several new architecture features that we're going to have to deal with, right? My mind goes back to when the GPUs were just coming out, which was a long time ago. I mean, they had come out for a long time before that, yeah, but no one had the means or the interest in programming them. So it was a while basically before, after they appeared in the market, that they got adopted and now are part of the large supercomputers and so on. What is the time frame for a similar adoption of these things that you're talking about here? Will we make the 2022 deadline?
Right. Well, so that's a very good question about how fast these will be rolled into chips that make it into HPC space. So the power-related ones, I think, are going in right away. I mean, even on BlueGene-Q, there are power-related features, and if you look at Intel's Knights Ferry, we showed you some graphs there. They're all thermally limited, right? And so Intel already has this turbo boost feature, right? And they will be able to add features that the programmer doesn't have to see for quite a while. They'll have code in the back that tries to guess, heuristically guess at how to manage the power. So the power management features, I think we're going to see right away. And are already showing up. The 3D chip stacking is a longer term. I think there's already been a couple products, real commercial, consumer products that have a little bit of that. But I think before we start seeing it in laptops where, you get rid of memory and it's all in the socket, it's going to be a while. Could be years before we see something like that.
You mentioned about DVFS and changing P states and C states. So we already know what sort of overheads are associated with changing P states for the entire chip. Are you allowed to comment about the overheads in that we should expect for per core P state changes or C state changes?
Yeah, so that's a good question. We haven't experimentally measured it yet. So I'd feel better once I experimentally measure it, because what the like with all of our power measurements, what they say and what we get are always, different. At least what they hope they have and what they get. So I'll ask our guys to take a look at how fast they can.
The question is, I don't know if that's what Usman meant, but is about the trend.
Yeah.
Is the trend downwards? Is the overhead going to go down?
The trend absolutely is downwards, and part of that comes from the number of power planes they have. So the number of areas of the chip that they can independently adjust power. It used to be that it was very monolithic, right? You would adjust power for everything, and then the reason it took so long is you have to wait for everything to get into a state that's okay with that, and that's not going to be the case.
Just a quick comment. The figure that you showed, where you were showing different domains for and the power readings. So I just wanted to make a quick comment. Some of the new Intel machines, first of all, they have a very low base power. Like the peak power is almost 5 times the base power, and they are very good in reducing the CPU energy consumption when it's idle. So from one of my experiments, it's as low as 10 watts, whereas the peak power for cores is 60, 70 watts when working at 100% utilization.
And that's what we're seeing as well. So this idle power was killing Intel in that, you know, their chips that they put out that they would say, you know, have these, you know, amazing abilities to change frequency and voltage. The idle power was, you know, the base power was 80% of total consumed power. Now they've changed these chips to be much reduced idle power, and then now we have room that we can play with algorithms.
I mean, that's what led people to say, and Kathy Ehrlich was fond of saying this,
right.
is that, you know, the best way of saving energy is run it as fast as you can and then turn off the machine. And that was true until a couple generations ago. And with Sandy Bridge especially, we see the shifting. Probably last or second last question.
So I recently read an article that talked about asymmetric core architectures, where you have like one big core and lots of tiny cores or something like that. So I didn't see you mention that.
Yeah, so
it's
a very fair question. There's been, and it's on one of my slides, sort of a picture there. There's been a lot of discussion that with more silicon than you can power, right? So you start with the idea that my thermal design point is let's say 40 watts, and I have more silicon than I can turn on. Well, then the natural result of that is to have specialized silicon, to not have all homogeneous cores, but have some cores that do something very well for their couple watts, and other cores that do something else very well and very GPU-like. And so there are some people who are designing paper designs right now that look at having, you know, FFT engines, you know, data parallel engines, you know, SIMD pieces and other things. You can't turn it all on, but, you know, you then would very purposefully have your code executing in heterogeneous areas, which may even have heterogeneous instruction sets, and that's where then I think, oh my gosh, we'll never figure that one out, right? But you know, where there's heterogeneous instruction sets on the chip, that will be very complicated. But it's certainly a possibility for the design.
You think it's longer term than?
Yeah. Aside from the GPU, which is in some sense a heterogeneous.
And SET, which already did that.
Yeah.
So you talk about internode parallelism and a lot about power. But usually when we build an exascale machine, so one debate is we try to run single application as fast as we can. So when we get to this scalability issues, most of the time it's not about a single node performance, but communication really kills the performance. So how do you think the interconnect will change, or will there any revolutionary change?
That's a good question. So these come back down to you know, Sanjay's the speed of light. I know what the speed of light is and how long it'll take to get from here to there. That area is going to be very hard to make, at least so far. It seems it's very hard to make major advances in. The best advance is bringing it closer and you know, making everything smaller so it has less distance to travel, but also reducing the number of places where it moves from copper to optics back to copper, right? So in these chips that they're now looking at having essentially an optical layer in the chip, there have been designs and been folks discussing designs where that optical layer in the chip could be extended for maybe one chip away. Well, now you could build a fabric, right? And then you could start, you know, reducing the latency between nodes. But that's pretty far off still. All of the 3D stuff that I pointed out so far in this presentation is based on not quite commodity, but pretty simple technology. They're thinning the wafers, they're stacking them, they're putting connections through. Another approach entirely that HP and others have worked on is that silicon is actually a very nice a very nice carrier for light. And they can build in silicon, they can build raceways, build little tracks where injected light essentially stays in this physical channel and can move in a ring around the chip. And so they can build a layer where one of the layers will be an optical, a photonics layer, and you would then be communicating among the cores essentially on an optical ring. That's further out technology, but that's the sort of technology that would then let you plug to something a little bit closer. But that's going to be, maybe 6 and 8 years away. Thank you very much.
Thank you very much.